Hello everyone, welcome to Snippet Today. In this video, we are going to discuss about recursion functions. We will see what is recursion function. We will see through some example how it works. We will also see what are call stacks and how recursion function flow goes through the call stack. We will also see what is recursion tree and how it is useful in calculating the time complexity. Also, at the end, we will see what is tail recursion, which is a very important topic. So please be with me till the end of this video and let us learn the recursion function. Before we start, I have a request, like if you can subscribe to this channel and like this video, it would be great. So let us start. What is recursion function? A recursion function basically calls itself inside the function body. This process of calling continues till the final result or the expected output is obtained. When the expected output is obtained, there is condition in the recursion function definition which exits the loop. That condition we call as base case or base function, base step. Okay. So as you notice, there are two important things in recursion function. One is it calls itself, and there has to be a base condition, which when met, the recursion function control exits the loop. Okay. Let us understand the working using a very simple example of factorial of a number. What is factorial of a number? It is basically the product from 1 to that number, okay, till that number. Yeah. So please remember, factorial of 0 or factorial of 1 is 1. Factorial of negative numbers are not defined. So if, let us say, we have to calculate the factorial of 5, it would be product of the number from 1 to 5, which would be 120 in this case. Okay. If we have to write a program to calculate the factorial of a number n in iterative way means non-recursive way. How we will write? We will write a simple for loop with I as a temporary variable, which will go from 1 to n, and we will have one variable called product, which we will initialize as 1 in the starting, and we will keep multiplying that product with I and the product so far. At the end, we will print the product as the final result of the factorial. Okay, so this is our iterative approach. In the recursive approach, what we will do is we will write this function as taking the integer number as an argument. Our base condition or the base step would be when n is equal to 1. It means we will check when the n is equal to 1, return 1. Why? Because factorial of 1 is 1. Okay, and we will keep multiplying the number n with a recursive call to the same function with n minus 1 as an argument. So basically, if we will see how it is working. So let us say if we are denoting factorial function with f and we want to calculate factorial of 5. When we are calculating factorial of 5, it will check whether 5 is equal to 1. No. So it will go to this else block. It will multiply 5 and call the factorial of 4. Again, it will come inside the same function. Again, it will check whether 4 equal to 1. No. So it will come to the else block. it will return 4 multiplied by factorial of 3. Again, factorial of 3 will be called. Again, it will come 3 into factorial of 2. Again, it will come 2 into factorial of 1. And then again, when factorial of 1 will be called, here 1 equal to 1. So this condition will be met, and factorial of 1 will return basically 1. So now the control will go back to factorial 2, and it will say that, hey, I have brought the result of this, and which is equal to 2 into 1, which is 2. So I have brought the result of factorial 2 as 2. So take it. It will be 6. Again, the control will go back to this, and it will say that, hey, I have brought the result of factorial 3, which is 6. Take this. So the control will go back to this. So 4 into 6 is 24. 24 is returned to this. Again, it will say that, hey, I have brought back the result. Take this. So 5 into factorial of 4 will be 5 into 24, 120. Okay. So in this way, factorial of 5 will be calculated as 120. So you can focus on this thing, that it keeps calling itself, it hits the base case, and it returns again one by one to the previous step. Finally, it fetches or returns you the output. This is how the control flows. We can try understanding this in a call stack way, but before that, let us see what are converging and diverging recursion. Converging recursions are those cases in which the control converges. Basically, your argument decreases to a point where the base case is hit. So the point here is that n decreases. This is called converging recursion because your n is converging to a point. Similarly, there is a diverging recursion in which your n increases to a point and then it hits the base case. But in most of the cases, we find ourselves using converging recursion only. Let us see example. For converging recursion, our same example of factorial is correct, where n is getting reduced each time in each of this step or the function calls. And at the end, when n is equal to 1, this time we hit this base case and we return back till the point where the initial function call happened. For the diverging recursion, let us take a simple example. If we have to write a function which will calculate the sum of all the numbers from a given number n till, let us say, 10. So how we will write that function using recursion? So for example, if we have to calculate sum of 5, so it means 5 plus 6 plus 7 plus 8 plus 9 plus 10. If we have to write sum of 1, then 1 plus 2 plus till the 10, like that. If we have to write a recursion function for that, how we will write? We will calculate the sum as follow. We will just see if n is equal to 10. If it is 10, then return 10. Otherwise, keep returning n plus sum of n plus 1. And we will call sum of 1 initially for calculating 1 till 10. So in this case, you can see that n is increasing at each step, right? N is increasing at each step. So basically, this function is diverging toward n is equal to 10. So this is a case of diverging recursion. Now let us move to the call stack. What is call stack? Call stack is basically programs memory in a stack format in which the program execution saves its state, that from where the state is flowing to where. Okay. In case of recursion, let us say in our program we are calling a function f1, which is calling another function f2, which is again calling another function f3, and so on. So in a call stack, what happens? Please remember this point very clearly, that in a call stack, 3 things are saved each time the program control moves from one function to another. Three things are saved. One is local variables, all local variables. Another is arguments. Okay, all the arguments that function was taking. And third is return address of the function. Okay, let us say if function f1 is calling function f2, so we need to save the state of function f1 so that when the control comes back from f2 to f1, we have the memory or we have the information that what was the state of f1. Okay, so we will save, let us say, all the local variable. If let us say we have two local variables, lv1 and lv2, we will save them or we will push them in the stack, lv1, lv2, or any more local variables if we have. We will also save all the arguments that function f1 has been taking. So we will save the arguments. For example, if f1 is taking argument arg1 and arg2, so we will save it in reverse order. First arg2 and then arg1. Okay. Why? Because when we are again popping it and coming to the control of f1, we will pop it in order of first arg1 and then second arg2. Then we will pop the local variable 2 and then local variable 1 by 1, all the local variables. And first of all, we will pop the return address of f1. Okay, why return address of f1? Because that is how we will reach where the f1 was executing in the past. Okay, so this is how we will save the state of f1. Exactly in the same way we will save the state of f2. Then we will save the state of f3. And when the control comes back to the f3, we will pop all the information of f3 and we come to f3. Then when we are coming back to f2, we will pop all the information of f2 and we will come to the running condition of the f2, and then we will come to the running condition of f1 in the same way. This is how the call stack works. Okay, so in the case of recursion, now you can visualize how it works. One by one, first let us say for calculating the factorial of 5, you will save the state of factorial 5. Then you will save the state of factorial 4. Then you will save the state of factorial 3. Then factorial 2. Then factorial 1. You will get the result that factorial 1 is equal to 1. You will come back to here. You will pop all the information of factorial 2. First, the return address of f2, then all the arguments of f2, then all the local variables of f2. Then you will get the information that, okay, what is the result of f2? You will return back to f3. All the information of f3 will be popped and f3 will be running, and so on. At the end, your stack will be empty. This is how it works. Okay, so this is all about the call stack. Now let us come to the recursion tree. I hope you have all the clear, like you do not have any doubts so far. If you have any doubts, please comment in the comment section and I'll be reverting back to it as soon as possible. Okay, let us move to the recursion tree. What is recursion tree? It is basically a tree diagram which shows how the recursion control is flowing. In using that tree diagram, it is very easy to visualize that how our recursion calls are flowing and what is the amount of work done at each step. It will be helpful in calculating the time complexity of that execution. Okay, let us take an example of binary search. This is an algorithm for binary search. It is a very simple algorithm. You will calculate the mid index each time, and you will see that if you have to search for a number, okay, whether that number is greater than or smaller than the mid index. If it is greater than, you will go to the first half. If it is less than, you will go to the second half, and you will call the same binary search function for this half part of the array. So in this way, you are basically at the end, you are finding what is the index of that number. If there is no index found for that number, we will return -1. Okay, this is binary search. So if you notice, the recursion mathematical representation of recursion here is something like this. At each step, you are dealing with, let us say, n-sized array. But at the next step, your problem is reduced to n by 2 sized array. So you can write it as tasks at one step is n sized array, but at the next step, or it is equal to n by 2 sized array plus some constant amount of task. Constant amount of task means comparing, assigning, calculating the made, all this constant amount operations. So in a way, you can say that at each step, your tasks are reduced by half. You can write your recursion tree something like that, that initially our task was Tn, but in the next step, it was reduced to Tn by 2 and some constant amount of operation. In the another next step, it is reduced by n by 4. Hence, again, some constant amount of operation. We can write it as C1, C2, C3, but because they all are constants, in the final asymptotic time complexity analysis, they all will be ignored because they are considered much smaller than n, where n is very large when we are calculating the time analysis. Okay. So in this way, we can see that this n gets reduced to 1 at the end. It is reduced to n following the steps where each time the n is reduced by or divided by 2. So let us see that this is a form of a tree, right? Where the height of tree, let us say it is h. So because it is reduced by 2 each time, so n is reduced to n by 2, then n by 4, then n by 8, then n by 16 till 1. So we can write it as that n is 2 to the power h. If let us say n is 8, so 8, 4, 2, and 1. So the size or the height of this tree is 3. So 2 to the power 3 is basically, sorry, 2 to the power 3 is equal to 8, where 8 is the number of, sorry, n is equal to 8. So we can write it as 2 to the power h is equal to 8. You take log both the sides, you will get h is equal to log n to the base 2. So in this way, we calculate the height of tree. And these are the number of operations overall. Because the first operation is reducing it to the n by 2, second operation is reducing it to n by 4, till the time we have reached that index where that number is found. So how many tasks are done? Equal to the height h. And what is h? Log of n to the base 2. So we can write the time complexity as big O of log of n to the base 2. So you see, using the recursion tree, we have calculated the time complexity of this binary search. Just for the exercise purpose, you can try to calculate the time complexity of factorial recursive solution. Okay, I am giving you one hint. It is the answer is time complexity is O of n. Let me explain also. In the factorial case, each time our factorial function is getting reduced to f of n minus 1 plus some constant time operation. So how the recursion tree will look like? Fn, it is getting reduced to fn minus 1 plus some constant, fn minus 2 plus some constant, and so on till f of 1, where it will return to 1. So it will go back, something like that. What is the depth of this tree? N, right? Because n is getting reduced to 1 each step, n. So that is why the time complexity is O of n. So this is how we use recursion tree for calculating the time complexity. Let us come to the final topic, tail recursion. What is tail recursion? Before that, you need to notice that what is the disadvantage of a simple recursion here. If you will notice, in a simple recursion, when we are going from n to 1, in case of factorial, let us say, each of the function calls will be pushed to the stack. and when it hits n is equal to 1, each of that function calls will be popped from this call stack, and then all final results will be obtained. So you will notice that n times the function calls are pushed and n times the function calls are popped. This takes lots of memory in the call stack. Also, it is a slower execution because you are basically, pushing, preparing all the blocks, pushing it to the call stack, and then moving to another function, then again popping one by one each of the function blocks having local variable arguments and return address. So it is like time consuming process. What is tail recursion? In tail recursion, we make a little extra effort such that the final results of the recursion function, whenever it comes at the base, so basically what we do is we try to return the final result of the recursion function. Please notice final result, okay, at the base condition. In our simple recursion example, we were returning just 1 at the base condition, right? And then we are going one step till we will calculate the factorial of 5 in our example. But in this tail recursion, what we do is instead of returning 1, we will return the final result. So exit of the recursion function at base condition is optimized by compiler also, and it's fast. We will understand how. Let us try to write the same factorial problem using the tail recursion. Let us say we name it as factorial tail. We take 2 arguments, n and multiplier. Initially, the multiplier will be 1. We compare n equal to 1 and return the multiplier if it is equal to 1. Otherwise, we will check this else block and we will call factorial tail again with argument 1 reduced now, n minus 1, and this multiplier as n multiplied by the multiplier. Okay, so let us say if we have to calculate the factorial of 5, we will call this recursion function like this: 5, 1. Initial value of the multiplier is 1. So when factorial of 5, 1 is called, it will basically again call factorial of 4, 1 multiplied by 5. So 5. Let us write it as 5 into 1. Again, for calculating this, it will call factorial of 3 into 5 into 4 into 1. It will again call factorial of 2. Oh, sorry. Factorial of 2, 5 into 4 into 3 into 1. It will again call factorial of 1, 5 into 4 into 3 into 2 into 1. But now this is 1, so what will happen? It will hit this base condition and it will return the multiplier, which is the second argument. So it will return this number. So please notice here, at this step, it is returning this number. It is not going back to this factorial tail again and again. So even though it is going to push factorial 5, 1, factorial 4 into 5, factorial 3 into 5 into 4 into 1 and all this, but at the end it is basically returning the final result. So because this function is no more in action, compiler will by itself, as a process of garbage collection, will pop out all these functions because they are no more called by anyone, they are no more referenced anywhere. So compiler pops them automatically. But because these days compilers are very smart, and with each version of the compiler we keep updating or patching the older version to improve the performance. These days what compiler does is, at the time of compilation itself, it recognizes that, oh, this is an example or this is a case of tail recursion. It is not going to call back its previous function's call. So there is no point in storing all these function calls into a call stack in the case of tail recursion. So as a part of optimization of compiler, in case of tail recursion, compiler doesn't save the state of the function into the call stack. It directly treats this case as a linear function call. It directly function of f comma 1 will directly call function of 4 into 5 into 1 5, and then it will directly call to function of 3 into 5 into 4 20. Then it will directly call function of 2 into 3 into 20 60, and it directly calls function of 1 into 120, and the 120 is returned. So you see, it will never go back to this process. Here it will return, and this recursion control will be exited. So this is how the tail recursion works. It is faster, it is useful as per the memory consumption by the program. So that is why it is much faster. So we have just seen the comparison of call stack of a simple recursion and the tail recursion. You can try to watch this video again if you have any doubt, or you can try to post any of the doubts or confusion in the comment section to get it clarified. So let us close this video because we have already seen all the topics in the recursion. If you want to cover any of the more concepts or the topics in any of these areas, please comment, and I'll definitely make sure to cover those topics. Thank you.